What would you think if when we talk about fusion? What is fusion? Yes. 融合，对不对？或者叫聚变、核聚变。But this is reality. There is a national ignition facility in the United States. This is a cartoon. There are 192 laser beams shining together onto a very small fuel, a very small fuel, okay? And the laser is so intense. For a single laser shot, there is 2 megajoules. So if you play with femtosecond laser, this is amazing. When you have 1 millijoule laser pulse, it's already very intense. But this is big M, this is not small m. Small m is milli, right? 10 to the minus 3. This is mega, 10 to the plus 6. 2 megajoule per pulse. Wow, it's very intense. And why do they need so strong laser beam? This is the field, DT field. D is Deuterium, T is Deuterium, 重氢啊，这个就是2个氢，这是3个氢嘛，重氢构成的，穿根刀 ，sorry 哈，穿根刀的燃料。You know, these are very light material, right? Hydrogen is the lightest material, and D and T is 2 hydrogen atoms. Or 3 hydrogen atoms, it's very light. But after shining with very intense laser beam, the density can be increased to 1 kilogram per centimeter square. It's very, very large, right? Think about the lead. 铅我们一般认为是很重的、密度很高的元素，对不对？ What is the density of lead? About 13 grams per centimeter square, right? And the compression reaches 1,000 grams per centimeter square, starting with the hydrogens, okay? Then ignition can be initiated. So that means it will release more energy than the input. And there is chain reaction. You got more and more energy, okay? And if this technology succeeds, basically you can create a sun on the Earth. Then you can have, in theory, unlimited energy without pollution, right? This is not like fission. If you use fission technology for power generation, you got big problem, like what we are suffering now, right? But if you use fission, basically there is no pollution, and the energy is, created energy is even more. Okay. The problem is, so far, the fission is only realized as a weapons, right? Because you need a traditional atomic bomb to do the ignition. And then everything is destructive. You cannot harvest any energy. Right? If you want controlled fission reaction, this is one of the possibilities, but not the only one. There are other possibilities, and some of them make even big progress than the laser approach, I have to admit. This is just one of the candidates. So I roughly show you the basic applications of ultrafast optics. Then we can move on to review. In section 1-2, we will review electromagnetism. There are many topics, but I will only remind you of 2 points, including equations and the solutions of electric fields and the Poynting vectors, because they are closely related to what we are going to discuss. Okay, let's start with the wave equation. We know vector electric field satisfies the wave equation in the time domain under certain conditions. And this is the wave equation. You must have seen this. Do you still remember how to arrive at this equation? Starting with 4 Maxwell's equations, combining them together, you can get this, right? But don't forget about when you arrive at this equation, you have assumed a lot of conditions. Do you still remember what are the conditions? The material has no source, like charge source or current source, right? Okay, anything else? If the conditions are violated, you cannot arrive at this. Okay. So source-free. What are the other conditions you have to assume?
Only one material.
Homogeneous, right. A pure material. Okay, that's right. So there is no spatial distribution. From one area to the other area, the material is the same. Okay, this is another assumption. What else? Linear. The material has to be linear. Well, what does that mean? What is linear material? When you increase the external electric field, the polarization response is proportional to that external field. That is linear. If it is not proportional, then it's not linear. You have new frequency components will be generated. Right. Here we assume it's linear material. Okay. Anything else? Maybe just one more. Isotropic, good. What does isotropic mean?
No direction vector.
Right. There is no direction dependence. If you look at the material in this way or this way or this way, you see the same material. Okay, so maybe glass is amorphous, is isotropic, right? Or liquid or gas should be isotropic, but crystals usually not isotropic. Then you have more complicated things to deal with. Here we assume, okay, nothing spatial. Then you have a simple wave equation, okay? But if we only consider phasor, do you know what is phasor? If you major in electrical engineering, maybe it's quite common, but maybe in other fields it's not so common. Phasor means when we talk about sinusoidal waves, okay, single frequency sinusoidal wave, you can forget about the complicated time dependence. You just replace a sinusoidal function with a complex number. The magnitude and the phase should be sufficient to represent the sinusoidal waveform. That is phasor. Okay? But here we talk about vector phasor. An electric field is a vector field, right? So the direction is preserved. But the time dependence has been simplified as phasor representation. In this case, the wave equation will be reduced to the so-called Helmholtz equation, this one. Okay. Do you know how to transform this one into this one? This one looks the same, so the secret is here. There is second order time derivative replaced by j omega parenthesis square, which is minus omega square. And omega square combined with mu 0 epsilon becoming k square. K is wave number, right? So you transform this one to this one, but be careful. The E vector here is a function of space and time. The E vector here is a function of space only, no time dependence. The time has been represented by the phasor itself. Okay, so the E vector here is a real function. The E vector here is a complex function. Okay, although they look the same, but they are actually different. If we further simplify to the case when the electric field is not only sinusoidal but linearly polarized, the plane wave. Okay, so the key words are plane wave and the linearly polarized. What is plane wave? A wave, when it propagates, the transversal direction is uniform. Nothing changes along the transversal direction. If you propagate along the z direction, there is no xy dependence. So you got an infinitely large cross-sectional area. Cross-sectional area. Okay, that is plane wave. And what is linearly polarized? Your electric field oscillate along a single direction. Okay? In general, the trajectory could be an ellipse, right? Tilted ellipse in general. Okay? But here we assume it's only oscillate at a single transversal direction, like propagation along z, but the E field is only along x or y. That is linearly polarized. Under these conditions, even Helmholtz equation can be further simplified to a very easy, very trivial, ordinary differential equation like this. Okay? Laplacian is reduced to second-order derivative with respect to z because we assume it propagates along the z direction. And the xy is uniform, no xy dependence. So there is no derivative about x or y because they will be zero anyway. And why should we focus on this simple case? Because you can easily get the solution like this. You have a complex amplitude represented by its magnitude and the phase. They are constant, right? Followed by an e to the minus jkz representing the propagation along z. Okay, this is the easiest, and we use it more frequently than other cases. Okay, so this is the general one, simplified one, even simplified one. And this is the most useful. Okay. Good. Second, pointing vectors. Pointing theory deals with the idea of intensity. Intensity is referred to power density. You can check the physical units. Watt per meter square, which is power per unit cross-sectional area. This is referred to intensity. And the pointing theory talks about the intensity. If you talk about instantaneous intensity of arbitrary electromagnetic wave, the arbitrary means not restricted to plane wave or sinusoidal wave. It could be arbitrary. Non-sinusoidal is okay. Non-plane wave is okay. Okay? Then the power density is a function of space or position and the time, which is E cross H. If you know the electric field distribution and the magnetic field distribution, the cross product between them gives you the pointing vector. And then you can know at any position, any time instant, what is the instantaneous intensity. So you can get the why E cross H gives you power density distribution. Although the result is quite easy, but why this is true? It comes from power or energy conservation. You use the enclosed volume. The output should be the same as input. Okay, try to review your textbook. Okay. So here we just borrow the result without proof. If you are interested in the proof, please review your textbook. But just like the logic of the previous slide, we try to simplify gradually. For example, if you focus on sinusoidal waves, then power density can be reduced to this one, but this is instantaneous. Here, we are only interested in time-averaged power density. We do not care about the oscillation. We are just interested in the average value. In this case, your power density vector or Poynting vector becomes 1/2 real part of E cross H star. Okay? But remember, now, E and H are vector phasors. Here, E and H are electric and magnetic fields. They are real functions, but these two are complex functions. They are functions of space and time, but here they are functions of space only. Okay? Then you can calculate the spatial distribution of your time-averaged power density with this formula. There is no time dependence because only time-averaged value is of interest. Okay. But it permits you have a non-uniform beam, like a Gaussian beam. Your power density is the highest at the middle and the decay along radial direction, right? This formula will take care of that case because it's not a constant, it's a function of position. Okay. How about if we further simplify the case to plane wave? Okay. If you talk about plane wave, there is no spatial distribution anymore. So average power density becomes still 1/2 real part E cross H star, the same thing. But in terms of plane wave, your H star is reduced to AK vector cross E star over wave impedance. Okay, let's check this point later. If this is true, you got a very simple formula. E0 epsilon square over 2 epsilon. E0 means the amplitude of your electric field phasor. Okay? Epsilon, according to this formula, is the wave impedance. And that's why last time we mentioned about why the electric field is related to the intensity and the wave impedance. It comes from this formula. Okay. But the question is why H can be represented by this one. Maxwell equation? Which one? There are 4. I borrow my hand to you. What is the equation you want to? Curl what? E equals B. Right? Am I wrong? Please correct me if I make a mistake. Okay. But here, E and B are electric field and magnetic flux density, right? They are functions of time and space. What is B? Usually we can write B equals mu times H, right? And if we restrict to, because here we are talking about sinusoidal plane wave, so we try to use phasor, right? Phasors. If you use phasors, partial T becomes this one, right? So then you got curl E equals, there is a minus sign here, minus J omega mu H. And the E and the H are vector phasors. Okay? But to this point, it's still unclear. Why is that? What should we do further? The right-hand side is already done. Nothing more. Secret is here. If it is plane wave, how do you operate curl? Operate with curl. Write down the curl equation in Cartesian coordinates, right? X, Y, Z. Partial X, partial Y, partial Z. And EX, EY, EZ, right? Do you still remember this formula? Okay, good. But if you are talking about a plane wave propagating along Z direction, they can be simplified, right? Is there any X dependence? So this is 0, 0. This is not 0. You have Z dependence. But what is your Z dependence? If you are talking about plane wave propagating along Z. Let me show you the previous slide. Here, this is your Z dependence. Right? So if you perform derivative with respect to Z, what would you get? Minus JK, then same thing, right? So in theory, this partial Z can be replaced by minus JK. That's it. Then just expand this one. You got X component 0 times EZ, so it's 0, minus JK, you got plus JK times EY and so forth. And then you got this, because curl E should be something like minus JK vector cross E. Proven by this operation. Okay? Okay, I think the remaining text is quite straightforward. Just practice, you can do that. The curl operation becomes a cross product operation with respect to your K vector, if it's about plane wave. Then you can make sure this is correct. Okay?